So in the experiment 4, we have learned about different types of inverters. Not different types of inverters, we have basically learned about push-pull inverter and edge-bridge inverter. If you seem to remember, in push-pull inverter, we used a DC source and at the output we got an alternating output. Right. How did we achieve this feature? Basically, we used these switches very smartly, or we controlled the switches in such a way that gave us this sort of output, right? The switches were controlled by different pulse generator, and basically we used MOSFET switches, if you seem to remember, right? The switches were configured in such a way, when S1 was conducting, S2 wasn't conducting, and when S2 was conducting, S1 wasn't conducting. So we created the system using MOSFETs, right? And in edge-bridge inverter we also used 4 switches, and these switches were configured in such a way, when S1 and S4 were conducting, S3 and S2 were not conducting, and when S2 and S3 were conducting, these two switches were not conducting, right? And this was made possible because we used MOSFET as switch and we had pulse generator. If we look at the Proteus circuit of the edge-bridge inverter, we can see the switches are something like this. And how these switches were configured? These were configured as simple MOSFET switches. When there was voltage between gate and source, we had our MOSFET shorted, and when there was no voltage between gate and source, we considered our MOSFET as open circuit. So this is a simple configuration of the MOSFET switches. Why? And one more thing, in edge-bridge inverter we have used a voltage controlled voltage source while configuring this switch and this switch. And why did we do so? I hope you all know, because this thing has been discussed in previous videos and in previous sessions, so I will not discuss about these things in this video. The business area that I want to discuss in this video is about the switches used in push-pull inverter, right? In push-pull inverter, if you look at the switches, here are the two switches we have used, and they are configured in a bit different way. So this is the pulse generator, and here is the voltage divider. That means some divided voltage will appear here between gate and source, but there's some extra portion, right? This is the portion we have used while configuring our switches. Now the question is, why have we used this portion, and what is the need of this thing? So in this video I am going to discuss about this thing, and this very thing is called RC snubber, and this is something that is used in power electronic circuits for safety purpose and for different purposes, and we will get to know what is the basic reason why this snubber is used and why have we used this snubber in this circuit. So let's dive into this. Before we start to know about RC snubber, we have to learn about some basic MOSFET switches. See, if this is a basic circuit and we use a MOSFET here as a switch. Now assume we have a voltage source of 10 volt and we have a resistor of 20 ohm. So what will happen? If we apply, let's assume 5 volt here in the gate of this MOSFET, this MOSFET will work as a short path, right? And the current will flow through this path, right? So if we look here, what will be the drain voltage? The drain voltage will be 0 volt for the same circuit. Now if the same circuit we are using here is a 10 volt source, but we are applying 0 volt here in the gate of this MOSFET. Consequently, what we will get an open circuit here, And if we want to measure the drain voltage here, can you guess what will be the drain voltage here? If we have used 10 volt source here, so the drain voltage will appear here as 10 volt. So we can say if we are using a pulse in the gate of this MOSFET, so when there will be some gate voltage available, let me draw the graph first. When there will be some gate voltage available, the drain voltage will be, of course, 0. When the gate voltage will be 0, the drain voltage will be equal to the source voltage, right? So in this way we will get the curve of gate voltage and drain voltage. So this happen in practical cases as well. This photo is taken from a practical case. See, when there is a gate voltage is 0, the drain voltage is in higher side, and when there's some gate voltage, that means the MOSFET is working as a short circuit, the drain voltage is obviously 0. So this is a very practical case, and if you implement the circuit practically, you will see this thing happen in practical case as well. The problem arises when we use a circuit of this sort. When we use our let's assume we are using an inductor in place of a resistor, and we are using a MOSFET which we want to use as switch. If we use this circuit in practical case, let's see what happens. When we use a circuit of that sort with an inductor and the MOSFET as a switch, what happens there? See, the relationship between the gate voltage and the drain voltage is something of this sort. What happens here? The problem is that we get a spike in the drain voltage when the gate voltage goes from high to low. See, this is the problem that happens in practical case. This will not in theoretical case we don't seem to face this thing, or in Proteus we might not face this thing, but in practical case this is what happens. And why this happens, let's see. In theoretical case, for example, we are using this circuit and we want to turn on this switch. So in order to do that, we have to provide some gate voltages. For example, we are using 5 volt here as gate voltage. So what will happen? This path will get shorted and current will pass through this path, so no problem. But if you seem to remember, inductor is a component that will store energy. If current is flowing through this path and flowing through this inductor as well, there will be energy stored here. As the current flows through this path, the energy stored inside the inductor will increase. The problem will arise when the MOSFET will work as open circuit. How it will work as an open circuit? If we apply 0 volt here, for example, in that case this will work as an open circuit. Now previously the current has been flowing through this path, and now this path is open. So can you guess what will happen to the current flowing through the inductor? Since inductors don't like this sort of situations, so it will force the circuit so that the current still flow through this inductor. As the current will flow through this inductor, what will happen consequently? The energy stored here will get increased. We can explain this situation in another way. If you it is evident that the current will flow through this inductor, so if the currents will flow through this path, so consequently electrons will flow in the opposite direction, right? In this point there will be deficiency of electrons, so in this setup, all the electrons will go or get stored here, and in this point the voltage will rise drastically, since there will all the negative charge will be stored here, and this point will work as positive voltage, and so at this point the voltage will be very high. I think you can relate here. When the gate voltage will be 0, here the drain voltage will be very high. I have shown you a photo of a practical case where you could see there was a spike in the drain voltage when the gate voltage went from high level to 0, right? So that is the case, or that is the reason why drain voltage will increase to such level. And if it does, what will be the problem? The MOSFET we have used in our Proteus circuit is of this model, and its datasheet says that the maximum drain voltage it can tolerate is 55 volt. So the case we were discussing, that when the gate voltage went from high to low, the what happened to the drain voltage? The drain voltage rise to some unexpected level, or we could see a spike in the drain voltage. If that spike goes above the 55 volt, that will permanently damage our MOSFET, right? So we cannot let that thing happen, and if we let that thing happen, our MOSFET will get damaged and the circuit will not work. And if the circuit will not work, we cannot get the desired output in our inverter, right? Because the output or the desired output we had in our inverter is all because we controlled the switches very cleverly. So all our efforts will go in vain if we cannot protect our switch, the switch that is very important in case when we are trying to get an alternating output from a DC input. So what we have seen in this case, what will happen, there will be excessive current flow, and excessive current flow will make the drain voltage very high, and there will be a surge of drain voltage, and that might damage our MOSFET permanently. So in order to avoid this situation, we must create a path here, and a path in such a way so that the drain voltage doesn't get too much high or get to that level that can damage our MOSFET permanently. So in order to create a path for this stored energy to get dissipated, we can create a path using a capacitor and a resistor here. So for that very reason, if you look at the Proteus circuit of the push-pull inverter, in the MOSFET switch we have used these two paths. Why? Because in any case, if there was an inductor, so when the gate voltage will go from high to low, there might be a possibility that the drain voltage would go to such level that might damage the MOSFET permanently. So in order to keep our MOSFET intact, in that case we will be needing a path from where the extra energy stored can be dissipated. In this particular circuit there is no inductor introduced here, but when we will be implementing this circuit in practical case, there can be some inductance involved beforehand of this switch. So it is not like that we have to use an inductor to get the advantage of these paths. Basically we can use these paths to protect our switches, and if our switches are protected, we can use our inverters properly. So that is the basic reason why we have used these two paths across the drain and source of our MOSFET switches, so that we can get the most efficient way, or we can use the switches most efficient way. So this video was about this, and thank you very much.